Hi guys, hope everybody is staying safe and healthy during this weird time with the coronavirus. Hope you all are social distancing. Hopefully we'll be back together very soon. Anyway, we'll be covering section 6.1 today out of the book, pages 312 through 322, and that covers the normal distribution. It is a famous distribution. It's one of the key things we learned about in the statistics class. So we got three objectives there. Number one, we want to look at theoretical properties of the distribution. So we'll look at kind of the definitions and information about this distribution. As far as actually doing math, we're going to find areas under the normal distribution curve using a z-table. And we're also going to use the normal distribution curve as a probability distribution curve. Okay, so we got three goals there in this video. So by the time we get through this video, expect that you'll be able to do those three things. Before we can get to those objectives, I just do want to run a very brief review of discrete versus continuous variables. A discrete variable, remember back from chapter 1, is a variable that can't assume all values between any two given values. Kind of a, hard definition, maybe wrap the mind around when it's written that way. A good concrete example here would be the number of ice cream cones ordered. If I go to Dairy Queen, it's possible for me to order no ice cream cones, one ice cream cone, two ice cream cones, so on and so forth, as many as I want, or as many as they have in stock. What I can't do, I can't order 1.5 ice cream cones. That's not possible. It does not make sense in the context of ordering an ice cream cone. And so if I look at the values 1 and 2, well, the number of ice creams ordered can't assume every value between 1 and 2. It can't assume any value between 1 and 2. It can only assume 1 or 2. On the other hand, the time is a continuous variable. Now, granted, stopwatches have limitations, usually the nearest hundredth of a second. But with an accurate enough stopwatch, you could theoretically run any time, for example, between 50 and 51 seconds. That's the difference there between discrete and continuous. In chapter 5, we looked at distributions for discrete variables. So we looked at the binomial distribution. We looked at other concrete distribution for discrete variables. In chapter 6, we're focused on only one distribution. That distribution is the normal distribution, and it deals with continuous variables. So with that, let's take a look at the normal distribution. Its graph has three key traits here. The graph is continuous, which means I can draw it without picking up my pencil. It is bell-shaped. It is bell-shaped, meaning it has this type of shape. It has short tails here at the end, and these tails extend forever and ever and ever, actually. But these tails are low, and it rises to a peak. Has a low tail to a peak, back down to a low tail. Same with these two. That is the idea of bell-shaped. So when professors talk about a bell curve, perhaps at the next level, this is what they're looking for, a normal distribution. And it is also symmetric. If you look at these black lines here, these black vertical lines, each graph is symmetric about one of those lines, which means no matter which direction I go from that line, the graph has the exact same shape. If I look at this particular line, blue goes down, 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 flat, down, 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 flat. Looks exactly the same. It's a mirror image across that line. Same with this brown one, and same with these two. Now you'll want to note that the shape of the graph is affected by two quantities. The first one is the mean, which is the average. Looking at figure B there, you can see the effect that changing the mean has. When I change the mean from 0 to 2, the general shape is identical. I mean, these two have the exact same shape. The difference is the brown one has been moved a little bit to the right because its mean is larger than the mean for the blue curve here. Likewise, if I had a smaller mean, if I wanted to go smaller, I would move to the left. So if I had mu as -1, it would just be, here's a vertical line right here, and I would just draw an identical curve. All the change in the mean does is it shifts it left and right. The other thing that affects it is the standard deviation, which is that measure of spread that we've talked about. How spread out is the data? The more spread out the data, the shorter and wider the graph will appear. Whereas the smaller the standard deviation, the more scrunched in the curve will be. If I look at this brown curve, it has a standard deviation of 1. It's kind of crammed in there tight. Whereas this one with a larger standard deviation is more spread out. It's wider. Okay, so those are the two things that affect the shape of the normal distribution. These properties, you want to just probably take a minute and pause it and write these down, or they're in your book. But it has 8 key properties there. The first is that it's bell-shaped. We went into that one in the last slide. I'm not going to go into that any further. You can see the general shape there. An interesting property here is that the mean, the median, the mode, those 3 measures of central tendency that we talked about in Chapter 4, are all the same, or Chapter 3 maybe. So if I think about this value of mu right here, that's the mean, that's also the median, and that is also the mode. Okay, so all 3 measures of central tendency there are the same value. Going further, it is unimodal. If I look at this graph, there's only one highest value. Okay, we think about probabilities. This is the highest probability. This is our mode, and there's only one of them. It has one mode. It's symmetric about the mean. All right, so we talked about it being symmetric. In particular, it's symmetric about the mean. Now, if you looked at those graphs on the previous slides, you could probably have told me that. I look at each of these 4 graphs. They're each symmetric about their respective mean. But that is a fact that is true. It is symmetric about the mean. It is continuous. There are no gaps in this curve. I can draw it without picking up my pencil. Number 6, it never touches the x-axis. Now, it comes down and it kind of flattens out, but it will never get down onto this x-axis. Theoretically, no matter how far I go, it's never going to get down here. Now, it's going to get really, really close. It can get as close as I want it to if I go out far enough on the x-axis. If you're in calculus, you're thinking maybe a limit here. But it can get as close to 0 as I want, but it will not get there. The total area under the normal distribution curve is equal to 1.00, or 100%. Which, if we think about this as a probability distribution, makes sense. The sum of the probabilities of any distribution must be 1. And so from a probability standpoint, it makes sense that everything under here would equal 1, or would add to 1, no matter what the mean is, no matter what the standard deviation is. And then the proof there is way beyond what we're going to do here. In a calculus class, we could look at it. It's a pretty complicated equation that gives this curve. That equation is in the book, but I spared you from needing to know it. You don't need to worry about that. And then finally, the empirical rules that I believe we discussed back in Chapter 3. Within 1 standard deviation is 68%. So if I look at, here's 1 standard deviation to the left, 1 to the right. I've got 34% plus 34%, right around 68%. Within 2 standard deviations, so from here to here, I've got about 47.7 and 47.7, so about 95.4, a little bit above 95, but we say approximately 95% of all data values within 2 standard deviations. And then finally, if I go out even further, 3 standard deviations, almost all of my data will be within 3 standard deviations of my mean. So my data for a normal distribution is relatively bunched. It's not going to be super spread out typically. Within 3 standard deviations, I will have 99.7% of my data. And you can see that here in this graph. Those are the theoretical properties of the normal distribution. Let's take a real quick look here at the standard normal distribution. The standard normal distribution is just a normal distribution whose mean is 0. So here mu is 0. It's symmetric around 0, so the median is also 0. The mode is also 0. We see these 68% are between -1 and 1 within 1 standard deviation. 95% are between -2 and 2, within 2 standard deviations, and 99.7% of all data values are within 3 standard deviations between -3 and 3. That is the standard normal distribution. Now you need to pause there for just a second and go on with that. I'm going to move to the next slide. So as far as uses, which we're not really going to look a whole lot at uses of it in this section, that's more 6.2 and 6.3. We're just going to look at how mainly to use the z-table, which we'll talk about here in a minute. But it is used for application problems. And again, we will see those in future lessons. As an example of what we may be able to do in future lessons, we might be able to figure out what percentage of adult women would have heights between 5'2" and 5'4". Now, we would need to know the mean and the standard deviation for the height of an adult woman. But if we know that, then we can find, what percentage would have heights between those two values. Now, going back to, I think it is chapter 3. In order to find these areas, we're going to need to use those z-scores that we talked about in chapter 3. So remember that your z-score can be found using the formula z equals the observed value, x, minus the mean. So the difference between the observed value and the mean, you divide that by the standard deviation. That is your z-score. How many standard deviations away from the mean am I? And so you will need to know that formula. We're going to make heavy use of that. Not as much today, but in future lessons, we're going to make heavy use of that formula. So now, how do we find these areas? That is the question. Now we're moving kind of into objective 2. How do we find these areas? You'll see there are 3 types of drawing that we may be dealing with when we find an area under a curve. We might need to find the area to the left of a z value. We're going to have a table. We'll deal with this table here in just a second. I'm going to show it to you. It's on pages 779 and 780, I believe it is. But it's to the left of a value. Then we're just going to look at the z value of the table. We're going to use the area that's given. That's the easiest version. That table will give you the area to the left of any given z value. If I want to look to the right of any z value, you're going to look up the z value, subtract the area from 1. That's because you're going to look up the z value. It's going to give you the area to the left of that z value. So when I look up a value in the table, it's going to be giving me the area in here, in this little unshaded area. Well, I know based on my properties that this entire area is 1. So to find the area to the right, that will be 1 minus the area to the left. Okay, the area to the left plus the area to the right is 1. Subtracting the area to the left, you get the area to the right is 1 minus the area to the left. And that could take place, over here with a larger area, over here with a smaller area. And then finally between, look up both values, subtract big value, big area minus small area. The reason for that is that we have the big area is all of this. Okay, from here all the way through here. The little area is only in here. But if I take both of these, I'm double counting. Okay, I'm double counting, so I need to find the area here, and I need to take out this area, because this area is not going to be shaded anymore. I could look at any number of things. You have it on either side, you have it both on the right, both on the left, but those are the 3 shapes. So as far as finding the area under the curve, there are 2 key steps. I can't stress enough how important it is to draw the picture here. You've got to draw the picture. You've got to get comfortable drawing the picture. Once you draw the picture, we can come back and we know what we're going to have to do. We've got these processes. But without drawing the picture, it may be difficult for us to recognize that. And then step 2, we're going to go back to that procedure table. We're going to just follow the directions. And it's 779, 780. Again, we are going to make heavy use of that formula, or of that table. And just to show you what that table looks like, it is right here. So it's got all these different z-scores. So here's, let me just zoom out just a little bit here. There we go. So, for example, if I want to look up the area for negative 3.14, I'd go to negative 3.1, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. The area to the left of negative 3.14 is 0.0008. Okay, we're going to get to know these tables really well. It goes from negative 3.49 all the way to positive 3.49. And it gives us this little tip down here. It also shows us what the drawing looks like. All right, so this chart's going to be super useful when we deal with this on a test going forward. You'll have that. But you are going to want to get to know this table and know how to use it very well. This is the standard normal distribution. It is on Moodle. It is in your book on page 779 and 780. Now, back into here we go. Let's take a look at some problems. So, we want to find the area under the standard normal distribution curve to the left of z equals 1.73. So, left of 1.73. I'm going to go ahead and transition to the board here, so give me just a moment here. Left of z equals 1.73. All right, let's try this again. Had some technical difficulties there. Sorry about that. Had to add it in the webcam, and for whatever reason didn't want to do that in the middle of a work problem there. So we're going to get started here. Again, find the area on the standard normal distribution that is to the left of z equals 1.73. And I'm just going to full size this if I can. I think I can. Yeah, cool. So to the left of 1.7, z equals 1.73. First thing I want to do, I want to go and I want to draw the picture. All right, so okay, so there's my bell curve. We're going to assume it's a standard normal curve. So right here is 0. Okay, a little bit smaller. I'll draw that a little bigger in the future. But to the so I've got it. I know that 1.73 will be over here somewhere. I'm going to draw 1.73. We'll just lay it, maybe right. So I got a z-score of 1.73 right there. And I want the area that is to the left of 1.73. All right, so looking at this drawing, look back at the procedure table there. We'll note that it's an area to the left, and so my procedure here was to just look at the value in the table and write it down. And so that's what I'm going to do. Let me make this just a little bit smaller. Escape from here. Shoot. I'm going to have to just open something real quick. Made a little bit of mess of myself here. Statistics, and it is right there. Here we are. So we're looking at 1.73 now. 1.73. I'm going to zoom out a little bit again. 1.73. So I scroll down into page 780. No, thank you. No, thank you. No, thank you. 1.73. So let me just scroll up just a skosh here. There we go. So 1.7 and 0.03 meet at 1.70. 1, 2, 3. 1.73. The corresponding value there in the chart is 0.9582. So relatively easy problem. We just have to draw the picture. If I draw the picture, it becomes a relatively straightforward problem. Now let's take a look at a different problem. Example 6.2. Area there to the left, to the right, I should say, of z equals negative 1.24. So to the right, z is negative 1.24. I want the area to the right of that. So I'm going to draw my standard normal curve once again. Doesn't have to be beautiful by any stretch. Mine's kind of crap there, but it works. We draw, again, we're assuming it's standard, so 0. I know that negative 1.24 will be to the left of that somewhere. Negative 1.24, and I want to shade everything in here. And so I'm looking there at a problem type number 2 from that procedure table. I'm looking at, and let me just a bit better. Looking at a problem where I need the area to the right. My procedure there is to, oh, can you even read that? I don't think you can read that. I guess I do need to move that a little bit closer, don't I? Maybe make it a little bit bigger. That would be smart, huh? Let's try that. That's better. Okay. Anyway, to the right of z is negative 1.24. I got it shaded to the right here. So I need to find the area in the table. That's going to tell me what's in here. But I want to know what's in here, so I take 1 minus whatever I find when I look in the table. So let's do that. Let's go into here. I'm going to have to just do this, I guess. Escape the standard normal table. Negative 1.24 this time. Let me just have feet and find that. Negative 1.24, so negative 1.2, 0, 1, 2, 3, 4. My answer here that I would write is 1 minus 0.1075, which is 0.8925 for that problem. Again, I subtracted from 1 because I wanted the area to the right. The table only gives me my areas to the left. That's why we had to go and do that. And again, I'll full screen that. I need to remember to do that, so get out of the way here. Sorry for the awkward technical situation here. Wasn't really sure how to do it given that I got a broken stylus right now. So we had, this came from the table. I subtracted it from 1. I get 0.8925. Let's try one more. So let me just make this small. This time I won't forget to make it big. So into here, Shift F5. So between 1.62 and negative 1.35. So between 1.62 and negative 1.35. So this one, and now I will make this full screen before I forget. Okay, gonna draw my bell curve. Got a slant there, but that's fine. Like I said, I don't need perfection. So it's standard, 0's in the middle. 1.62 is gonna be over here. Don't need any precise scaling or anything. Negative 1.35 will be right here. And I want to find the area in here, right in there. And so my procedure here, referring to the procedure table, was I wanted to find the area to the left of the big one, subtract the area to the left of the small one. So I got to look at 2 different spots in my table. So let's go ahead and do that real quick. Have a seat here and table. So 1.62, 1.60, 1, 2, so 0.9474, 0.9474 minus, now I got to look at negative 1.35, go into my negative z values, negative 1.3, 0, 1, 2, 3, 4, 5, minus 0.0885, 0.0885. That needs a calculator. I'm going to have a calculator real quick. So 0.9474 minus 0.0885 the value there is 0.8589. All right, so that is one each of the types of problems in the procedure table, which is, again, go back a couple slides here, just looked at one each of this type of problem. Oops, that's not what I wanted to do. There we go. So we looked at one to the left, one to the right, one between. Most of your assignment this week will consist of problems like this. Let's see here. Now we can also think of it as a probability. Same idea. So when I give you a problem written like this, it is the exact same thing as I can rewrite it in a way like this. So I want to find the probability for each. And again, we're assuming it's standard normal. So let's say I want to find the probability that z is greater than 0 and less than 2.53. So let me just real quick write that down, and then I'll go on to the big screen here. So probability 0 less than 2.53, I believe was the value. Make myself a little bigger here. There we go. So probably 0 is less than z is less than 2.53. So what that indicates as far as a drawing, all right, so here's 0. 2.53 will be kind of way out here in the tail. Oops, mistake. Eraser. Glove is the next best thing. I'll take it. 2.53. There we go. And I want to find the area between these two numbers. So this is going to be kind of a situation number 3 there from the procedure table. I want to find the probability that I'm between here. I can do that again by looking up the area to the left of 2.53 minus the area to the left of 0, which I know is 0.5, by the way. I don't even need to look up that in the table. Because I've got symmetry. Got symmetry here, so if these two add up to 1, half will be on the left, half will be on the right. Now, it is going to be in the table, I'm pretty sure. But that's just one of those things where you can look at a shortcut. So I'll take a look. It should be in the table. So let's see. Let's first look up 2.53. So 2.53, so 2.5, 0, 1, 2, 3. So that's 0.9943. 9943 minus looking at 0.00, 0.5000, 0.5000. Put myself back in full screen, and that is equal to 0.494, not a 9, oops, 3. All right, so I found the area to the left of the larger value, the area to the left of the smaller value, and I subtracted those two things. Okay, so there's part A knocked out. Let's go into small screen for just a moment while I get ready to write the problem. Come into here, right there, shift F5. So probably now that Z is less than 1.73. Okay. Probability less than 1.73. Full screen so you can see what's going on. We draw the bell curve once again, so I'm drawing my curve. There's 0 in the middle. To the right, 1.73 I know will be, it's bigger than 0, so it's going to be over here somewhere. And if it's less than, I want Z to be smaller than 1.73. Well, less than indicates I'm going to shade to the left. I'm going to shade to the left here. I want to know that probability, that area. And this one's just as easy as looking it up in the table. This is going to be right there in the table for me to look at. I can find that pretty quickly. Let's do that. Let's put this back in the corner. And 1.73, 1.70, 1, 2, 3. Didn't we have that value just a second ago? That is equal to 0.9582. And that one is then done. Okay, nothing more to do on that one. In full screen, you can see it there a little bit better. It's 0.9582. One more of these. Greater than 1.98. Okay, so let's put this in full screen. Greater than 1.98. So we draw the chart. If I'm greater than, I'm shading to, I want to know what is the area in that small table. So I expect it to be pretty small, by the way. I don't expect a lot of area there. And so what I need to do, I need to look this up in the chart, but then subtract it from 1. Remember, I want to find the area to the right. So I find the area to the left over here. I subtract that from 1. It's going to be 1 minus something. That something is in the chart. 1.98. Let's partial screen this. 1.98, so 1.90. 1, 2, 3, 4, 5, 6, 7, 8.9761, I think that says. Yeah, 0.9761. Which is 0.023. So just over 2% is the probability there of falling in that small area. You can see it there in the full screen. I'll lean back just a little bit here. But we found the area to the left using the table. We subtracted that from 1 because I wanted the area to the right. With, I think we got one more slide maybe that I want to look at. So let me just partial screen this, just because I have gotten a little bit longer than I wanted to be, honestly. Let's see, so right in here. One more, we'll stop after 13. So find the z-value such that the area under the curve is 0.2123. Okay, so let me full screen this just real quick. So we need to find, next slide. There we go. So find the z-value such that the area under that standard normal distribution curve between 0 and that z-value is 0.2123. All right, so let me just go into full screen here. This is a little bit different. This is going to be kind of a reverse lookup. Instead of searching, like hunting the z-value and finding the probability, we're going to be hunting for a probability. Man, I got hiccups here. So find z area between 0 and z is 0.2123, I think. I can't move that, so real quick, click here, 0.2123. Yep, okay, back to full screen. Sorry for the roller coaster there. So let's draw a picture here. Here is my z. Too skinny there. But 0 and z is in here is 0.2123. So this one's different in that I don't know a z-value yet. That's what I'm asked to find. And I don't know it yet, so I'm going to have to do a little legwork here to find this. So let me try to write this in terms of that probability notation we were writing in the last slide. I could write this prompt. Really what it's telling me is it's saying that the probability that 0 is less than z is, oh, well, shoot. I'm going to make a different z here. Needs to equal 0.2123. All right, the likelihood that my z value is between 0 and big Z here needs to be 0.2123. Well, this is a between problem, so I can do this with algebra. I could do with algebra, although what I'm actually going to do, I'm going to do a little bit simpler, I think. Again, going back to this idea of symmetry. I know that on each side of this line, there is 0.5. So the area here adds up to 0.5. Likewise, the area over here must add to 0.5. So I know that the area over here is 0.5000. Now, what do I need to do with that information? Well, that means that in this entire area, there's the 0.5000 here, there's the 0.2123 here. I add those together, the total area to the left of Z needs to equal 0.7123. So again, I'm going to do a reverse lookup here. I'm going to look for 0.7123 in my chart, and wherever I find it, that is the given Z value, or that is the Z value that I want to find. So just to recap that again, I was asked to find the probability that between 0 and Z was 0.2123. I knew this part was 0.2123 as given in the problem. I also knew that half of my data would be over here, just by the definition of the normal distribution there. Add those together. I'm now going to look it up in the table. I'm going to look this up in the table. So I'll do that. So looking for 0.7123. So where do I find it? 0.7123. 0.7123. Let's see here. This is all points bigger than that. Too big, too big. Too small, too small, too small, too small, too small. Hey, just right. So that occurs 0.7123. What a happy coincidence. At 0.51 or 0, 1, 2, 3, 4, 5, 6. 0.56 is my target value. That's it for now. For now, I'm going to stop right there. I need to get back home and kind of relax a little bit, but I will look to probably do the other additional examples here in the next couple of days. This should be enough to get you started on this, which again will be posted shortly. Shouldn't be too long before I get that done. Hopefully in the next 24 hours after making this video. Anyway, have a great rest of your day. Thank you for tuning in, and I will see you again hopefully very soon.